Tokyo, 1938. Japan was moving rapidly toward total war. Military planners understood that the country's fate would not be decided by numbers alone, but by engineering precision. Lacking the industrial depth of the United States and the resource base of the European empires, Japan placed extraordinary faith in technical skill. Aircraft performance became a national obsession. Speed, range, maneuverability, and aerodynamic efficiency were expected to offset material shortages and limited production capacity. Universities, research institutes, and military laboratories were pulled directly into this effort. Among the engineers drawn into this system was Hideo Itokawa, a young specialist whose career would be shaped by the demands and contradictions of wartime aviation. Born in 1912, Itokawa came of age as Japan was transforming itself into a modern technological state. He studied engineering at Tokyo Imperial University, one of the country's most elite scientific institutions. His academic focus was aeronautics, a field that combined mathematics, physics, and mechanical design at a time when aviation was still rapidly evolving. His training emphasized theoretical rigor, airflow behavior, structural stresses, propulsion efficiency, and experimental verification. This foundation placed him among a generation of engineers who approached aircraft not as craftsmen, but as systems governed by calculable laws. By the late 1930s, Japan's aviation research infrastructure was tightly integrated with military needs. Itokawa joined the Aeronautical Research Institute at Tokyo Imperial University, where his work focused on aerodynamics and flight performance. Rather than working on complete aircraft designs, he specialized in understanding airflow characteristics, stability, and drag reduction. His role reflected a broader shift in Japanese engineering philosophy. Instead of relying solely on incremental design changes, researchers were attempting to refine performance through scientific analysis, wind tunnel testing, and mathematical modeling. During the war years, Itokawa contributed to studies connected to several Japanese military aircraft programs, including high-performance fighters. Japan's aircraft designers faced severe constraints. Engines were underpowered compared to Allied counterparts. Fuel quality was inconsistent. Production tolerances were limited by shortages of high-grade materials. These realities forced engineers to extract maximum performance from airframes through aerodynamic refinement rather than raw power. Itokawa's work addressed precisely these issues, focusing on reducing drag, improving lift efficiency, and understanding control behavior at high speeds. The most famous Japanese fighter aircraft of the era, such as those developed by Mitsubishi, were the product of this environment. While Itokawa was not a chief designer of operational aircraft, his research fed into the broader ecosystem that supported these designs. His studies informed decisions about wing profiles, structural layouts, and flight characteristics. This distinction is important. Wartime Japan did not rely on isolated geniuses, but on tightly linked networks of researchers, whose findings were distributed across multiple projects. Itokawa was part of that network, operating at the level of theory and experimentation rather than factory-scale production. Despite these efforts, Japan's aviation industry struggled to keep pace with Allied advances. As the war progressed, the gap widened. Allied aircraft benefited from powerful engines, radar integration, advanced metallurgy, and mass production techniques. Japanese engineers understood these shortcomings. Many, including Itokawa, were acutely aware that their scientific solutions were being applied within a system that could not fully exploit them. Aircraft designs became more refined, but strategic limitations remained. By 1944, the situation grew increasingly severe. Air raids disrupted factories and research centres. Resources were diverted toward defensive measures. Experimental work became difficult, sometimes impossible. Yet research continued, often under austere conditions. Engineers documented findings, refined theoretical models, and preserved knowledge for a future that few could clearly imagine. Itokawa continued his academic and research activities, maintaining a focus on fundamental principles rather than short-term fixes. This emphasis on theory would later prove decisive. Japan's defeat in 1945 brought an abrupt end to this entire system. The aviation industry collapsed overnight. The Allied occupation imposed strict prohibitions on aircraft development and related research. Laboratories were dismantled. Military-funded programs were terminated. Engineers who had devoted their careers to aeronautics found themselves professionally adrift. For Itokawa, the war had ended not with triumph or recognition, but with the sudden disappearance of the field he had spent years mastering. Before we continue, if you value historically accurate documentary storytelling that goes beyond myths and examines how technology truly shapes history, remember to like the video and subscribe to the channel to support future episodes. This first phase of Itokawa's career reveals an engineer formed by a system that demanded scientific excellence while offering limited room for strategic success. He was not a weapons designer in the popular sense, nor a propagandist figure. He was a specialist in aerodynamics, operating within a constrained industrial and political environment. The end of the war stripped away that environment entirely, raising a question that would define the rest of his life. How could an engineer trained for military aviation reinvent his work when flight itself was no longer allowed? The war ended, not gradually, but absolutely. With the Emperor's surrender, Japan's military and industrial systems collapsed in a matter of weeks. For engineers who had worked in aviation, the impact was immediate and devastating. The Allied occupation authorities imposed a total ban on aircraft development, production and research. Wind tunnels were shut down. Design offices were dismantled. Technical documentation was confiscated or destroyed. Aeronautical engineering, once a national priority, became a prohibited discipline. For Hideo Itokawa, whose entire professional identity had been built around flight, this was not simply a career setback, but a complete erasure of purpose. Like many former wartime researchers, Itokawa faced suspicion. Engineers associated with military technology were viewed as relics of a defeated system, and in some cases as potential threats. Funding disappeared, and institutional support vanished. Universities were forced to abandon entire departments. Research that had once been encouraged was now forbidden by law. For several years after the war, Japan was not allowed to possess aircraft of any kind, even for civilian use. Within this environment, Itokawa's expertise in aerodynamics had no obvious place. Rather than resist or attempt to preserve the old structures, Itokawa adapted. He remained within academia, redirecting his attention toward fields that were permitted under occupation policy. He taught mechanical engineering and applied mathematics, focusing on foundational principles rather than specific applications. This period was marked by restraint and discipline. Instead of designing machines, he concentrated on theory, education, and the transmission of scientific knowledge to a new generation of students who had grown up amid defeat and reconstruction. During the late 1940s, Japan began a slow process of economic and intellectual recovery. Restrictions were gradually relaxed, although aviation remained heavily controlled. Scientific research returned cautiously, framed increasingly in civilian and peaceful terms. Itokawa observed these developments closely. He understood that any future work connected to flight would have to avoid military association entirely. This realization would shape his next steps. Rather than returning to aircraft, he began to think about rockets not as weapons but as scientific instruments. At the time, rockets occupied an ambiguous position in global consciousness. They were associated with German wartime weapons, particularly the V-2, yet they also represented new possibilities for high-altitude research and atmospheric science. In the United States and the Soviet Union, captured German technology was being repurposed to study the upper atmosphere and cosmic radiation. Japan, by contrast, had no access to foreign rocket programs and very limited resources. Any domestic efforts would have to start from almost nothing. Itokawa's interest in rockets was cautious and methodical. He did not possess a vision of space exploration in the popular sense, nor did he promote grand ambitions. His focus was practical and scientific. Rockets, he reasoned, could reach altitudes inaccessible to balloons and aircraft, allowing researchers to gather data on temperature, pressure, and radiation. Framed in this way, rockets could be presented as tools of pure research rather than military instruments. This distinction was critical in post-war Japan. In the early 1950s, small-scale experiments began under severe constraints. Funding was minimal, equipment was often improvised. Early test rockets were tiny, sometimes no larger than a pencil, designed primarily to test propulsion and stability rather than payload capacity. These experiments were conducted discreetly and academically, avoiding public attention. Failures were frequent, and progress was slow. Yet this incremental approach suited Itokawa's temperament. His wartime experience had taught him the limits of ambition in the absence of industrial support. Equally important was the institutional context. Japan's scientific community remained fragmented, and centralized coordination was weak. Unlike the United States, there was no single agency driving rocket development. Itokawa worked within universities and research groups, building credibility step by step. His insistence on transparency, civilian goals, and international scientific norms helped shield these efforts from political backlash. Over time, this approach fostered trust, both domestically and abroad. By the mid-1950s, attitudes towards science and technology in Japan had begun to shift. Economic recovery was accelerating, and national confidence was slowly returning. The government started to see scientific research as a symbol of rehabilitation and modernity. Rocket experiments, once marginal, attracted cautious support. Still, expectations were modest. Japan was not competing with superpowers. The goal was participation, not leadership. Itokawa understood this reality and worked within it, avoiding claims that could provoke resistance. This period marked a decisive transition. Itokawa was no longer an aeronautical engineer serving military objectives, but a scientific organizer seeking to establish entirely new foundations. The skills he had developed before and during the war remained essential: aerodynamic reasoning, experimental discipline, and an understanding of constraints. Yet the context had changed completely. What had once been applied to fighters and engines was now directed toward research rockets and institutional frameworks. As Japan emerged from occupation and began redefining its scientific identity, Itokawa stood at the boundary between prohibition and possibility. He had survived the destruction of his field, adapted to years of restriction, and quietly prepared for a future that did not yet officially exist. The question was no longer whether Japan could build aircraft or weapons, but whether it could define a peaceful technological path of its own. Could these fragile, improvised experiments become the foundation of a national space effort? Japan, 1955. The transition from cautious experimentation to organized scientific ambition marked a turning point. By the mid-1950s, Japan had regained limited sovereignty, and with it came a renewed desire to participate in advanced research on equal footing with other nations. Rocket experimentation, still modest in scale, began to receive formal recognition as a legitimate scientific pursuit. For Hideo Itokawa, this moment represented the convergence of preparation and opportunity. Years of theoretical focus, academic patience, and carefully framed civilian objectives were now becoming institutional reality. The early rocket programs under Itokawa's guidance were deliberately conservative. The pencil rocket, followed by the baby rocket, was designed not to impress, but to verify. These vehicles tested propulsion stability, structural integrity, and basic control behavior. Their small size was not a limitation, but a strategy. Limited budgets, restricted facilities, and an absence of industrial partners required designs that could be built, tested, and modified quickly. Each launch produced data rather than spectacle. Failures were logged, analysed, and treated as progress rather than embarrassment. As confidence increased, more advanced designs followed. The Kappa series represented a significant technical step forward. These rockets achieved higher altitudes and carried scientific instruments to collect atmospheric data. This phase marked Japan's first sustained entry into upper atmosphere research using domestically developed launch vehicles. While these achievements remained far behind the capabilities of American and Soviet programs, they were not intended to compete directly. Itokawa's approach emphasized reliability, reproducibility, and scientific usefulness over scale. Crucially, these efforts helped solidify an institutional framework. In 1964, the Institute of Space and Aeronautical Science was formally established, with Itokawa playing a central role. This organization consolidated previously scattered research activities and provided a long-term foundation for Japan's space science. Unlike military-driven programs elsewhere, ISAS operated under explicit civilian and academic principles. Its mission focused on research, education, and international collaboration, reflecting lessons learned from both wartime constraints and post-war prohibitions. Itokawa's leadership style was shaped by experience rather than ideology. He avoided grand speeches and nationalistic rhetoric. Instead, he insisted on methodological rigor and incremental progress. Young engineers were trained to think in terms of systems, limits, and verification. International cooperation was encouraged, particularly through the open sharing of scientific data. This approach helped integrate Japan into the global research community, while maintaining political acceptability at home. By the late 1960s, Japan's rocket program had matured into a stable, scientific enterprise. Larger solid-fuel rockets, expanded payload capacity, and research objectives diversified. Studies in astrophysics, atmospheric science, and space physics became routine. These successes were cumulative rather than revolutionary, built on decades of careful groundwork. Itokawa's influence was embedded not in individual machines but in the culture of the institutions he helped shape. The title often associated with him, the father of Japanese space science, is not symbolic. It reflects a concrete historical role. He did not launch satellites himself, nor did he oversee dramatic firsts comparable to those of superpower programs. What he did was more fundamental. He defined the principles under which Japan could pursue space research legally, ethically, and sustainably. He translated pre-war aeronautical knowledge into a post-war scientific framework that avoided militarization while preserving technical excellence. His legacy extended beyond engineering. In a country rebuilding its identity, Itokawa embodied a model of responsibility. He demonstrated how advanced technology could serve peaceful purposes without denying its origins. This balance proved durable. When Japan later unified its space activities under larger agencies, including what would become JAXA, the institutional DNA established under Itokawa's guidance remained evident. Emphasis on reliability, safety, and research integrity became defining traits of the Japanese space program. Itokawa retired from active leadership as Japan's space activities expanded, but his influence continued through the systems he left behind and the people he trained. His career traced a unique arc, from wartime aerodynamics through enforced silence to scientific renewal. Unlike many engineers whose work was bound to a single era, his contributions adapted to radically different political and ethical landscapes without losing coherence. If you found this exploration of how science survives defeat, restriction, and rebuilding valuable, like the video and subscribe to the channel for more historically grounded documentaries on the people who shaped modern technology. Hideo Itokawa's life challenges simple narratives of progress. It shows that innovation is not always driven by power or competition, but sometimes by restraint, patience, and structural thinking. His work did not place Japan first in space, yet it made participation possible on its own terms. The final question remains one that extends beyond history. How many modern technologies owe their existence not to dramatic breakthroughs, but to individuals who quietly redefined what was allowed, achievable, and worth pursuing?